see how much you can accomplish in a short time. All right, so as I said, we're moving on to a new topic, right? Um, this topic is one of my favorites, and it is very easy. That's why it's probably one of my favorites, right? So we want to distinguish between specific heat capacity and heat capacity. No, what does that sound like? What does heat capacity sound like? Somebody want to give it a try?
Sir, the amount of heat something hold.
Level of
Right.
heat, sir.
Yeah, essentially. Very easy stuff, right? So it's the amount of heat that something can hold, capacity, heat, right? Or the amount of heat that it takes an object to really raise its temperature. So the ability for an object to hold the heat. So if an object can hold a lot of heat, it will take a lot of heat, a lot more heat to raise its temperature than a regular object. So if say water is able to hold more heat than alcohol, you'll find that it will take a lot more heat to raise the temperature of water than it would take to raise the temperature of alcohol. And I think that makes sense to me. I understand that, right? So we should know that specific heat capacity and heat capacity are related by the formula. We'll go through that, apply the relationship of apply this particular relationship, and we want to determine the specific heat capacity of metals and liquids. This is a particular lab that we'll do, and we'll discuss this further. All right, we'll discuss this further. Now, before we go, though, we have to look at the kinetic theory of matter, right? The kinetic theory of matter, we had two theories. We had the caloric theory and we had the kinetic theory. So the caloric theory states that heat is considered a fluid that flows from a hot object to a cold object. So when they are in contact, when a cold object and a hot object is in contact, you'll find that the object gets cooler, the hot objects get cooler, and the cold object gets hotter, right? People once believed
So
that,
you go warm, sir.
yeah, yeah, so it's going to get the colder object is going to get warmer, right? And people believe that it's heat is a fluid, right? And we know that heat is not a fluid, but people once believed that just because it flows from a hot object to a cold object,
Sir,
right?
so heat not coming off from steam.
Steam is from the actual liquid. So you'll find that we'll talk about that in a few seconds, right? But the heat, when you see heat coming off, all right, for example, you're boiling water and you're seeing steam, the steam is actually water, right? Which is carrying the heat, right? And you will see in a few seconds that heat is considered energy, and it's considered when objects have a lot of heat, you find that they have a lot of energy, and the particles in those objects move very vigorously, right? So you'll see that in a few seconds, right? Friction causes the buildup of small particles and more caloric, right? So as I said, they believed that that heat was some form of fluid. And when we rub against something, you find that you're right. I'm rubbing against the chair now, and I'm finding out that as I rub against the chair, my hand begins to get hot. People thought that it was building up of caloric or small particles, right? Building up of that small caloric, and that was the thing that's causing the heat. But we know that's not true. That's not true. All right. So we move now to the kinetic theory. This is what governs, right, the behavior of heat. And the caloric theory says that all atoms have some form of motion, no matter what, right? All atoms in whatever object you're looking at, in your bed, in your computer, all atoms have some form of motion, they exhibit perfectly elastic collisions. What does this mean again? Remember this? elastic collisions. We spoke about this a few weeks ago.
Uh,
Same.
When the objects collide, what happens? They stick together or they bounce away from each other.
Bounce away.
Right. So elastic meaning that they bounce away. And all atoms therefore have kinetic energy. No matter what anyone wants to say, right? We can prove that all atoms have some form of kinetic energy. So heat is considered the kinetic energy of moving atoms. Heat is what causes atoms to move. That's what we want to try and say. So heat is what causes atoms to move. So when mechanical work is done, the heat energy is referred to as heat produced by friction, right? Whenever we're doing any form of work, right? If there's the car is running and the wheels and the hinges at the wheels are constantly in motion, right? You'll find that heat is produced. All right, you'll find that heat is produced in that particular section. So caloric theory, if the caloric theory was true, when an object gets hotter, it gains caloric, right? Remember that we said that caloric, they consider caloric a fluid, right? But whenever an object gets hotter, its mass remains the same. Its mass does not change. But if it was a case where caloric or heat was considered a fluid or caloric, right? You find that the object would get heavier, right? So if the caloric theory was true, when an object gets hotter, it gains caloric and therefore additional substances, right? And there is no evidence to prove that as the object gets hotter, it gets heavier. There's no form of that, doesn't even make any sense, right?
So it's a question.
Yeah,
So like when like say one metal ball, sir,
yeah.
and when it cool, it can go to one iron rim, but when it get heat up, it can't go to one iron. It can't go to the iron rim. Me see them do an experiment when we did a research on topic in physics,
Yeah.
but
So,
me no know, me no understand.
all right. So it gets bigger then. That's what you're trying to say. The
Yes,
metal ball.
sir.
Right. So what is happening is that it's not that a mass is added. There's no additional substances. What happens is that you'll find that the metal ball begins to expand. That's what happens. So whenever atoms get energy, you'll find that they begin to expand. We'll do an experiment in a few seconds just to prove that. Right? Whenever
Hot.
objects get warmer.
Expand.
Hear your question?
No, yeah, say when the atoms them get hot, them expand.
Yeah, essentially. All right. So let's go through this and then we do our experiment, right? Yeah. So after this we do the experiment and then we prove that. So then we can see from the kinetic energy, right? It was proven by the Brownian motion experiment. Let's talk a little bit about that Brownian motion experiment. Have you ever heard it before? From chemistry?
No, sir, I've never heard of that.
All right, so we'll have to create another slide then about Brownian motion, right? So Brownian motion is not, I don't believe it's required for CSEC physics, but essentially what happens was that um Mr. Brown, the person who came up with the experiment, right? He observed light coming through a window. And like in your bathroom, you're looking through the window and you see some small particles, right? You can see them.
Oh, like the sun a shine
Oh,
and
oh yes,
it a
sir.
grow. Yeah, yeah.
Yeah. So when he was
Yes, sir. We are right already, sir.
when you
And it come like, you do it on the flashlight, so.
yeah, and when you're looking at the object, when they're looking at the particles, you see that they're moving randomly and they're colliding. It seems as if they're colliding with some much smaller objects, right? That proves the kinetic theory because it is simply saying that atoms are everywhere, right? Atoms are everywhere in every situation. You have air particles, you have particles that we're not able to see, and the particles that we can see, they are the ones that collide with these particles, right? So, as I said, large molecules of a fluid have random motion. So you saw, looking through the window, you see some small particles, they have random motion, right? Which proves that they are small particles with varied kinetic energies and speed that is constantly colliding. They're colliding with these larger objects. They're colliding with these larger objects. If they were not there, you would find that the objects would move in a straight line. That's what we want to achieve, right? So even if these particles are moving randomly because of the breeze, right? Right, you find that particles are also in the breeze or in the wind that is causing these objects to move randomly. So therefore, all molecules have some form of motion. These molecules are not at one place. They're always moving, right? They never stay at one place. They're always changing direction. All right, so we'll just skip over to the experiment for a few seconds.
Like atoms and matter have nothing in common.
Yeah, so matter is essentially made up of atoms. Atoms is the smallest
Particles.
yeah, atoms are the smallest particles. So we have matter.
No, sir.
That's not the case.
Sir, what
So
about
far, no.
quark? What
We don't
about
have,
quark, sir?
we don't have no technology we can go no far.
I'm not hearing the question. Repeat again.
So they don't have no technology we can go further atoms.
Oh yes.
No.
Yeah, there is no technology that can. You're correct, right?
Sir, so what about quarks, the binders of atoms?
I don't have much information about that. If I must be honest, right?
Yeah, the man.
Yeah, yeah, but I know of quarks. I've heard about them before, but I know that in order for us to um, observe the behavior of matter, the best way that we can do it is by observing atoms, right?
Yes, sir.
And let me see if I can bring this up.
Hey, Walden.
All right. So this is our object we see. All right, let's put this in degrees. And all right, please observe this. All right. We haven't done Kelvin as yet. We haven't looked at Kelvin as yet. Mm, all right. So all right.
Yeah.
All right. So let's talk about Kelvin for a few seconds. All right. So Kelvin is that temperature, right, at 0 kelvins. See if I can bring it on to 0. Yeah. So at 0 kelvins, it is said that particles stop moving. There's no movement of particles. Right?
Oh, me about
Yeah.
this already, sir.
At 0 kelvin. Now,
Okay.
if we place it, so currently this is in a vacuum, and we have a thermometer here, looking at the temperature of neon in this. All right, let's change it to water. All right,
The particles start moving.
so let's put it back at 0 kelvin. What is this? All right, I'll fix that afterwards. All right, so at 0 Kelvin, we find that particles will stop moving. They won't change, right? It takes a lot of energy to get it to 0 Kelvin. All right, so no scientist has ever brought the object of
Oh,
the temperature of an object to 0 Kelvin, right? It's just an extrapolation, right, of the actual temperature. But you find that water stops moving at 0 Kelvin. Now, if we bring this up,
sir, hold on, sir.
it's
Dry ice
currently
melt.
hmm?
Dry ice melt.
Dry ice
Sublimate.
melts.
Like if I just put it down.
That
Sublimate.
that's not
Change
what we're
what?
talking about now. But it
I
doesn't
change
melt.
what?
Carbon dioxide.
It changes from solid to gas immediately. All right, but that's not what we're talking about now.
Got your water bunny.
All right, so if we see that the objects don't change, the particles don't move because it's at 0 Kelvin. Now, if you put it in a solid form, let's look on the degrees Celsius. Let's put it at 0 degrees Celsius. It's in a solid form. We see that the particles are closer together. So the objects are always in random motion, right? Always in random motion. As I said, no one has ever brought the temperature of an object to 0 Kelvin, right? Or not that I know of. You can go ahead and do your research. But I know for a fact that particles, even ice, right? Water is in a solid form. Ice is at 0 degrees Celsius, and the particles are constantly moving. They're not staying still. Why? Because they have kinetic energy. That's the kinetic energy theory. This is the kinetic theory of motion, which says that atoms are always in constant random motion, right? If we put this to a liquid, right? If we bring it up to say 13 degrees Celsius, we see that the particles are much farther away than when they were in a solid form. So they're now in a liquid form. And now if they're in a gaseous form, you see that the particles are much, much, much farther away. All right, you see that particles are much farther away. Now we can therefore move to a specific heat capacity. So as we apply heat, we will see that there will be a change in temperature. Let's just look at that quickly. Put it in a liquid form. It's at 13 degrees Celsius. If we apply heat, right, you see that the temperature begins to change, right? So the specific heat capacity is the ability of the object, as someone says earlier, to hold energy, right? And it is a measure, right, of whether of how much heat it requires for an object to raise its temperature. That's essentially what we want to accomplish for that experiment.
So, Mr. Treasure,
Question, yeah,
Kelvin,
not here, no.
Kelvin, Kelvin is the SI unit.
SI unit for what?
Kelvin.
For Kelvin? Yeah, Kelvin is the SI unit. But we'll talk about that in a few. All right. So we have temperature in degrees Celsius and we have temperature in Kelvin. All right. So we look firstly on heat capacity. All right, and this says that the heat capacity of an object is the amount of heat energy that is required to raise its temperature by 1 Kelvin or 1 degree Celsius. No, if you're having misconceptions about Kelvin, right? 1 Kelvin, right, is the same magnitude of 1 degree Celsius. Now, how we convert from Kelvin to degree Celsius, you'll find that most of the calculations that you do in thermal physics are done in Kelvin, right? So for thermal physics, whenever we're doing calculations, of course, for heat capacity, you won't need to necessarily convert, But as we move on to like gas laws and so forth, move further down into thermal physics, you'd have to change, right, it to Kelvin. Now, to convert degrees Celsius to Kelvin, you have to add, right? You have to add 273. All right.
Sorry,
In a
repeat.
second. Question?
Repeat where this is at.
Yeah, just give me a second, please. Thank you. Let me respond to this person. Yeah, no. Yeah, so I was saying that most of your calculations, you will have to convert degrees to Kelvin, right?
Sure.
So you'll add. I hear a question.
No, me right up. Here did that required top.
Oh, this should be 273.5.
So EE this even today.
Where?
It's a required top rise. Is it TE measured by 1 Kelvin.
Yeah, this should be 2.
Like or 2.
Yeah, the energy required to raise. Yeah, I'll fix that when let me just fix it now before I forget. Keep. All right. All right. Yeah. So to convert degrees Celsius to Kelvin, you would add 273. All right. So
Yes, still wrong.
temperature in Kelvin. You were saying something again?
Never mind.
Hmm?
Never mind.
All right. Now, to calculate heat capacity of an object, heat energy over the change in temperature. So that's why for heat capacity questions, you don't necessarily need to convert to Kelvin, right? I am just putting this out there for the future. All right, for the future references, you won't necessarily need to convert to Kelvin because 1 Kelvin is the same thing as 1 degree Celsius. All right, do you understand that?
Yes, sir.
Yeah, so 1 Kelvin is essentially the same thing as 1 degree Celsius, but you'll find that most of the calculations require you to convert to Kelvin because it relates the point at which or the temperature at which the particles stop moving, right? We don't do that in degrees Celsius. We don't consider that, but we consider it in Kelvin. That's why it's so important. All right. So for formula, we have heat capacity as C, big C, and heat energy, E to the H. Temperature rise, you have delta T right here, delta T. This is delta, and remember what delta means again?
Triangle, I think.
What does it mean? It means a change, right?
Yes, sir.
Yeah. So the change in temperature. All right. And we'll do some more questions. So most of the times you're required to give the temperature that we are give the amount of heat energy that is required to raise the temperature of an object. That's most of the times you'll get questions like these. All right. Now specific heat capacity. So specific heat capacity. All right. There's a error here again. Uh, but is essentially the amount of energy that is raised to the temperature of 1 kilogram of an object by 1 Kelvin. All right, let me add that in. Let me add that in as well. So specific heat capacity of an object is the amount of heat energy to raise 1 kilogram by 1 Kelvin or a degree Celsius. Yes. All right. So what is the difference here between specific heat capacity and heat capacity? What difference are we seeing? Hello?
Hello.
What difference are we seeing between heat capacity and specific heat capacity?
Times mass, sir.
Right, so mass is involved in specific heat capacity, and you'll find that we lose specific heat capacity a lot more than heat capacity. All right, so that is it for this particular class. We'll do some questions, right? We'll do some questions for the next class. So C,
What is JK?
JK, right? So the unit, yeah. So we'll have to come back after this then. All right. So we have less than a minute. Yeah, we have less than a minute. So let's close this and use the same link and rejoin. All right.
All right.